Welcome to Hot Chips 31. Session 6, ML Inference.
So for the next section, we have three papers, three presentations on inference. The first one is from Nvidia, and the speaker is Ranga, and he is a senior research scientist at Nvidia. He received his bachelor degree from the IIT Roorkee in 2009, and his PhD degree from ECE department from Purdue University in 2014. His research interests include machine learning accelerator, high-level synthesis, and machine learning for EDA. And he has been a member of the technical program committee for several leading IEEE conferences, including ISRCC, DAG, and ISOPAD. Let's welcome our speaker. Yeah.
Thanks, Ivan, for the introduction. So in this talk, we are presenting the first multi-chip module-based deep learning inference accelerator. We demonstrate high scalability from 0.32 TOPS to 128 TOPS, and demonstrate high energy efficiency of 0.11 picojoules per op. This design was implemented using a high productivity design methodology that enables faster time to market. So this work is from Nvidia research, and we are showing a research test chip, and it's not a product prototype. Nvidia research has a number of different research areas, and we regularly build test chips to demonstrate those ideas. This work is from our latest test chip that was taped out last year called RC18. We highlight two key contributions in this work. First, we show a scalable architecture for deep learning inference. We show that it is possible to design one architecture and scale the performance from edge to data center scale. We demonstrate high performance per watt at different scales. Second, we showcase a high productivity design methodology where we use the best practices from the software world in the hardware design process. So why do we need them? As we all know, deep learning finds applications across a wide range of applications and market segments, from edge to data center scale. Recent years have also seen the emergence of several new applications. While the applications continue to grow, the demands of these applications vary significantly. Designing custom inference accelerator for each market segment can lead to significant benefits. However, such a design incurs high ASIC and verification design effort, and this makes it challenging to design such point solution. To address these challenges, we propose a scalable inference accelerator design and a high productivity design methodology. In this work, we consider the image classification using convolutional neural networks as a target application. Our design is flexible to evaluate neural networks of varying sizes and complexity. Also, our system is configurable to evaluate MCM configurations of different scale and demonstrate the scalability of our design. The main goal of this work is to design a scalable deep learning inference accelerator. In this work, we demonstrate a multi-chip module-based approach and architecture for realizing this. The basic idea here is to build a single chip and assemble a varying number of chips to achieve scalability. The figure on the right here shows the overview of the prototype system. Each chip has 16 processing elements, or PEs, a global PE, a RISC-V controller, and interconnect macros for chip-to-chip communication. We assemble 36 of these chips in a package to design a large-scale inference accelerator. This prototype system achieves three key objectives. First, we demonstrate low-effort scaling for high inference performance. Each chip can individually act as a deep learning accelerator for edge inference. By assembling a large number of chips in the package, we achieve data center scale throughput. Second, for implementing efficient MCM interconnect, we propose a ground reference signaling-based approach. Third, we demonstrate a network on package architecture that enables us to connect all the chips in a single package. Now, it is possible to design a scalable inference accelerator using a monolithic approach. However, we have several advantages of adopting MCM-based approach. First, we can overcome the reticle limits without requiring board-level integration. The smaller chips will have better yield. Smaller chips are also easier to design and therefore have lower design cost. Further, MCM-based approach also gives us the flexibility to mix process technologies, which enables reuse and lowers cost. It also provides agility in changing the product SKUs. We can easily design a new inference accelerator by assembling the existing chips at the package level to design a accelerator of optimal size. However, this has certain challenges. This is primarily arising from the fact that chip-to-chip communication is more expensive than on-chip communication. To address these challenges, we explored two key optimizations. First, we propose a hierarchical communication architecture consisting of network on package and network on chip. At the network on chip level, the NOC connects 16 PEs, the global PE, and the RISC-V controller using a 4x5 mesh topology. It uses cut-through flow control for deadlock-free routing in the hierarchical network. It also has multicast support to enable reuse within the network and enhance the bandwidth. In terms of performance, our NOC router achieves 10 nanoseconds per hop and a bandwidth of approximately 70 gigabits per second at 0.72 volts. And this value scales depending upon the operating voltage. At the network on package level, we connect the 36 chips used in a 6x6 mesh topology. The architecture of the NOP router is very similar to that of the NOC router. A single NOP router has 4 ports that connect to the NOC to balance the bandwidth. And it also has configurable routing tables to avoid bad links or bad chips if we have one. It achieves 20 nanosecond latency per hop and has 100 gigabits of per link bandwidth. This hierarchical network on chip architecture has a number of advantages compared to a flat network that you can realize by simply connecting the edges of the NOC to adjacent chips. First, it results in lower latency. This is because a pass-through traffic can cross a chip in a single hop, which will require multiple hops in a flat network. Second, it reduces the congestion in the network. This is because the chip-to-chip traffic does not interfere with the on-chip traffic, resulting in lower congestion. These benefits enable us to improve both the performance and energy efficiency of the network architecture and realize better quality of results. The second aspect for achieving a scalable multi-chip module-based deep learning accelerator is to have efficient chip-to-chip interconnects. In this work, we used ground reference signaling. This is a novel technology from the circuit research group at Nvidia. It offers very high bandwidth and high energy efficiency. Each of this link consists of 4 data lanes and a forwarded clock. Each pin offers up to 25 gigabits per second of bandwidth, and therefore, each link can offer up to 100 gigabits per second bandwidth. We use single-ended signaling instead of the differential signaling. This enables us to use single bump and achieve high area efficiency. Further, each transmitter sends a small voltage swing signal of approximately 200 millivolts around the ground, and this enables us to achieve high energy efficiency. We have 4 such transmitter-receiver pairs in each chip to communicate with the 4 neighboring chips in the mesh network. Next, let's look at the chip architecture. As I said before, each chip has 16 PEs, a global PE, RISC-V controller, and chip-to-chip interconnect macros. The global PE primarily acts as a second-level storage for activation. It offers a high bandwidth interface for memory and is highly banked. In addition, it also has certain compute components that enables us to perform computations with low memory to compute ratio without sending the data to the PEs. The RISC-V controller acts as a global controller at the chip level. It has a memory mapped registers that sends control signals to configure all the PEs and the global PE. It also controls the synchronization for layer-to-layer computation. And the figure on the right here shows the microarchitecture of the PE. Conceptually, it is a scaled-down version of NVDLA, which was presented at Hot Chips last year. Each PE consists of a weight buffer, input buffer, vector MAC units, accumulation buffer, a post-processing unit, and router interface to connect to the NOC. The heart of the PE is the vector MAC units. We have 8 lanes of vector MACs inside a PE. Each vector MAC performs an 8-wide dot product, taking 8 input values and 8 weight values, and producing a single output value. Each lane of the vector MAC unit takes different weight inputs and produces 8 different output values. Optimizing the energy efficiency of these buffers is key to achieving energy efficiency in this PE. The input buffer is read every cycle, and we reduce the energy consumption by broadcasting it across all the vector lanes. The weight buffer supplies separate data to each of the vector lanes. Its energy efficiency is improved by adapting a weight stationary data flow and temporarily reusing the weights across a number of cycles. The accumulation buffer performs a read, modify, write operation and is accessed every cycle. Its energy efficiency is improved by spatially accumulating the partial sums in the vector MAC unit before writing them into the accumulation buffer. The PE is designed to be flexible to allow for reduction across the processing elements, and it has input and output ports that connect directly to the network on chip. Once the accumulation is performed, we perform post-processing elements in the PPU unit, and then send the output activation back to the global PE. To illustrate the functioning of the system, let us consider the execution of a convolutional neural network layer on a single chip. First, we load the weights and distribute them across the different PEs. We then load the input activation into the global PE. Then the RISC-V configures the different control registers in the PEs and the global PE, and then sends a start command to initiate the computation. We then perform the convolution operation by streaming the input activations from the global PE to the local PEs. And once the computation is complete, we send the output activation back to the global PE. Now, to achieve scalability in this design, we offer the flexibility of different tiling strategies. Here, I would like to illustrate one such tiling strategy that is based on model parallelism. Again, let's consider a convolutional layer and consider a system that has 4 chips. First, we divide the weights along the input channel and the output channel dimensions and distribute across different chips. We also tile the input activation along the input channel dimension and multicast it to chips with matching input channel dimension. We then perform the convolution operation and compute the partial sums inside in each chip. To perform the reduction along the input channel dimension, we transmit the partial sums from the chips on the first row to the chips on the second row. And the second row finally performs the post-processing and computes the output activation. We adopt a similar strategy to tile the computation at the chip level. We again tile the weights along the input channel and the output channel dimension and distribute across the PEs. Similarly, tile the input activation and multicast it along the row of PEs. Once the computation is being performed, we reduce the partial sum along the columns and compute the output activation. By temporarily repeating this along the P and the Q dimension of the output activation shown in the figure, we compute the entire output layer. Now, in this example, I have shown a very simple case where the multicast is performed along the rows, the reduction is performed along the columns, and we are exploiting model parallelism. However, our system is very flexible to exploit several different tiling strategies using the NOC and the NOP networks. And we support both model parallelism as well as data parallelism to enhance scalability. The figure here shows the fabricated MCM-based accelerator. We taped it out in TSMC 16 nanometer technology. Each chip is 2.5 millimeter by 2.4 millimeter and has all the components, including the processing elements and the GRS macros. We assembled 36 of these chips at the package level to achieve data center level scalability. We demonstrated high-speed interconnect links using ground reference signaling, which achieves 100 gigabits per link. We achieved high compute efficiency with an energy efficiency of 9.5 TOPS per watt and a peak performance of 128 TOPS. The chip has a high operating voltage ranging from 0.52 volts to 1.1 volts and an operating frequency range of 0.48 gigahertz to 1.8 gigahertz. In addition, we realized this chip with a very low design effort, and the spec to tape out took 6 months with less than 10 researchers. Next, I would like to describe the high productivity design methodology that enables us to achieve reduction in the design effort. There are two key aspects to the high productivity design methodology. First, we raise the design level of abstraction for the hardware design process. We designed this entire system using high-level languages in C++ and used automation tools to automatically generate RTL using high-level synthesis. We use libraries and generators for exploiting reuse in the design process. And we have designed a library called MatchLib, which consists of commonly used components and enables reuse in the design process. The second aspect is agile VLSI design. Here, small team of researchers jointly work on different aspects of the design, including architecture, implementation, and VLSI simultaneously. We adapt agile project management techniques and continuous integration with automation tools and achieve 24-hour spins from C++ to layout. We call the front-end design methodology as object-oriented high-level synthesis. It enables push-button flow from C++ to gates. Here, we code both the design and the test benches in C++ and System C and perform most of the verification tasks using C++ simulation. Both functional verification and performance verification are performed using C++ simulations here. And we use high-level synthesis to automatically generate the RTL. We have significant reuse in the design process. We have designed and open-sourced MatchLib, which is a library of commonly used microarchitectural components. They are highly configurable, pre-verified, and highly optimized for quality of results. You can imagine MatchLib as STL or Boost, and it is available open source via Nvidia GitHub website. Another aspect of this approach is latency-insensitive based design. It brings modular to the design process by decoupling computation and communication. This enables us to design each unit individually without worrying about the other units in the design. These techniques enables us to achieve the reduction in design effort of less than 6 months from spec to tape out. To demonstrate the reuse and modularity in the design process, we show the implementation of a processing element here. PE consists of a number of different units, each performing different functionalities. Each unit individually has a hierarchy of subunits. At the bottom of the stack, you can see the matchlab components that are reused widely across the design. We also use different coding styles to implement different blocks. Simple feed-forward blocks, or like the data path units, are implemented as C++ functions. Units with state are implemented as C++ classes. And units that have control logic are implemented as System C modules. We also leverage the high-level language features to design custom C++ libraries that are specific to the design, like the address generators and the buffer managers that are reused within this design. In this way, we achieved significant reuse and modularity in our design process. The next aspect is the agile VLSI design technique, which enables us to achieve daily C++ to layout sprints. We achieve two key goals using this approach. First, we enable fast and iterative feedback to the architects from different stages of the design process at different levels of fidelity. Second, it enables a large number of trials during our march to tape-out phase to perform QoR optimization as well as bug fixes. We achieved this by using small partitions, efficient clocking schemes, and developing an automated flow from C++ to layout. In this technique, the RTL bug fixes, performance optimization, and the VLSI constraints all converge together during the march to tape-out phase. Next, let's look at the experimental results. The figure here shows the measurement setup. It consists of the package along with a custom PCB board, which has clock generators, voltage regulators, and appropriate power measurement circuitry. The package talks to a Xilinx FPGA board, and which in turn connects to the host PC via PCIe Express. The FPGA fabric implements an AXI protocol with a global memory map that enables the RISC-V processor on the package to access the FPGA resources, including the DRAM. To perform an inference operation, we load a RISC-V program into the DRAM. The RISC-V then accesses the program and loads the input activation, weights, and the control registers into the chip. All our measurements start after the weights and input activations are loaded, and we present results for both maximum performance and minimum energy in the following slides. First, let's look at the weak scaling results for DriveNet. Here, we scale the batch size along as we scale the number of chips. So both the amount of computation as well as the amount of compute resources scale as we scale the number of chips here. The figure on the left shows the performance results of both throughput and latency. As we can see from the figure, we achieve almost linear scaling as we scale the number of chips. We achieve 27x speedup in throughput as we scale from 1 chip to 32 chips. And this is achieved without incurring much penalty in the latency. When we look at the energy efficiency, there are two key components. First, we have the GRS energy, which represents the energy consumed by the GRS macros for chip-to-chip communication. And then we have the core energy consumption. If we look at the core energy, we see that it almost remains constant across the number of chips, which demonstrates very high energy efficiency. However, as we have more and more chips on the package, we see that the energy consumption from the GRS increases. There are two main reasons for this observation. First, the GRS links always remain active, even when there are no chip-to-chip communication and the chip-to-chip communication traffic is bursty. Second, as we scale the voltage to 0.5 volts and reduce the energy consumption of the cores, the GRS remain active and start contributing a larger fraction to the total energy consumption. However, it is very easy to address this penalty by implementing a GRS sleep mode. Next, when we look at the strong scaling, here we are presenting the results of ResNet for batch equal to 1. The figure on the left shows the performance. As we can see from the figure, scaling the number of chips results in improvement in both throughput as well as latency. We achieve 12x improvement in performance as we scale the chips from 1 chip to 32 chips. And we observed that the communication for overhead for communicating across 32 chips, and the synchronization overhead for synchronizing all the components in a large-scale system presents a significant overhead and limits the speed up achievable by the system. In terms of energy efficiency, we observe a small overhead in core energy as we scale the number of chips from 1 chip to 32 chips. However, across all the scales, we are able to demonstrate quite high energy efficiency. To summarize this presentation, we have presented a scalable inference accelerator chip. We showed the use of MCM-based approach to address different markets with a single architecture. We demonstrated the results showing high energy efficiency as well as high performance. We achieved over 2.5K images per second with less than 0.4 millisecond latency for ResNet 50 with a batch size of 1. We also showed a high productivity design approach that enables faster time to market and can enable more features into each SoC. We achieved over a 10x reduction in ASIC and VLSI design efforts using this approach. Finally, I would like to acknowledge all the people who have supported in this effort. I would like to acknowledge the sponsors, for DARPA, for supporting us under the CRAFT program. I would also like to acknowledge the collaborators at Nvidia, and as well as the Catapult HLS team for their support. And this concludes this talk, and I'm happy to take any questions.
All right. Please, as a reminder, please keep your questions short and to the point. And to be fair to everyone, 1 question per person, please. Left side, please. Yeah.
Hi, YK Chen from Alibaba Damo Academic. I have a question about your result slides, because actually you 2 result slides showing you scale from 1 chip to 32 chips. But one of the slides actually shows that you actually changed the batch size from 1 to 32. And so in this case, when you scale from 1 to 32, do you actually distribute different images to different chips, or do you still only 1 image at a time? So I'm a little bit confused why you still have such high NOP energy consumptions.
Right. So to answer the first part of how we tile it, the tiling strategy varies from layer to layer in the network. Different layers use different tiling strategies. Some give better results with model parallelism. Other layers are more scalable with data parallelism. So depending upon the layer dimensions, we actually use different strategies. As we scale the batch size, it gives us better, more amount of computations to scale. And this enables us to achieve better scalability. However, it is not a single approach where we broadcast images to all the 32 chips. It is possible that we perform multiple images on the same chip for some layer, but different images on different chips for some other layer. Next, to answer the question on the energy consumption, that is primarily because our GRS didn't have a sleep mode because it was a research chip. And it was always on, irrespective of whether there is communication between chips or they are idle. By implementing the sleep mode, that energy consumption can be significantly reduced.
Okay, great. Thank you.
Get that one first. Go ahead, please. Left side.
Yeah, just about Kongung University. Thanks for the presentation. You have mentioned the latency insensitive communication together with the latency insensitive channel with the system C. Can you please elaborate on that a little bit?
I didn't get the question, second part.
The latency insensitive channel with the system C, does it have anything to do with the system C transaction level modeling?
Oh, I see. So it is enhancement over the transaction level modeling in system C. We have developed a library called connections library as part of the matchlib, which provides a latency insensitive channels at the system C level. And we use it in the design process to decouple the computation and the communication. And there are further benefits to this approach. Each unit now can be designed independent of the other without making any assumptions on latency or throughput of the other units. And this implies that we can reduce the design time and effort in the design process. And that helps to achieve faster time.
Go ahead, please.
Jeff Smith, Citadel. Question about the routers, the NAC routers specifically. So the number was 10 nanoseconds per hop, give or take, at gigahertz-ish frequencies, I guess.
Right. So we achieved about 1.1 gigahertz at like 0.72 volts. The hop-to-hop latency includes the latency within the router, as well as the latency that you incur from partition-to-partition interfaces, which have other.
Can you briefly describe the pipelining structure of the routers themselves, and maybe the design space you guys explored for your project on that?
Okay, so it's a very standard router architecture where you have a set of input FIFOs, and it uses a credit-based flow control, and then you have route computation being performed, and then you have arbitration. Depending upon whether it's a multicast traffic or a unicast traffic, you have different arbitration schemes and flow control. Subsequently, you basically have the outputs being pushed into different things. And we prioritize multicast over unicast, because for the multicast traffic, we need to ensure that multiple ports are available to forward the traffic. To have better fairness in the design, we prioritize multicast over the unicast in the router design.
Okay, thank you.
One last track question, please.
Thank you.
Yeah.
Nathan Brookwood, Insight 64. Can you give us some insight into the physical structure of your multi-chip package? Was it a silicon substrate, organic, or whatever?
It is based on an organic substrate. However, our approach applies to different package structures, interposers, or EMIBs, or other things. We chose to demonstrate that it is possible to design a scalable inference accelerator by scaling using this MCM-based approach at the package level. That was our main contribution. But
so you were more concerned with MCM than you were with exactly how you physically implemented it?
Right, yes.
Okay, thank you.
All right, let's thank our speaker again. The next presentation is from Xilinx, and the speaker, Sagheer, is Senior Director of Architecture responsible for SoC architecture at Xilinx. Let's welcome our speaker.
Thanks. So here's the outline we'll follow. Give a quick overview of what's Versal series, and then we'll go into the first Versal device, which is the focus of the talk. We'll go into the key building blocks of first device, and then we'll do a deeper dive of AI Engine. We'll share some performance numbers related to AI Engine, and then the software and the tools are related. Just to give some background, Xilinx invented FPGA back in like 80s. More recently, we have introduced heterogeneous integration of SoC into FPGAs. That's our Zinc products. For us, the next big architecture leap is ACAP. And ACAP are these devices which are defined to be or architected to be adaptable at accelerating different type of workloads. To do that, not only we need programmable logic, but we also need higher compute density. We also need high-performance interconnect, which can be customized. We also need the memory hierarchy, memory subsystem, which are high-performance but can be customized. We'll go over some of those today. And the Versal is our first series of ACAP type of devices. So before we go into the first Versal device, a quick overview of the Versal series as a whole. For compute, we have different compute engines which are connected through customizable interconnect and memory hierarchy. And the different devices will have different ratio and size of these engines in Versal series. All of Versal devices will have hard and NOC and memory subsystem, where we will support the latest DDR, LPDDR, and HBM memories. And we'll support latest high-speed interfaces such as PCI up to Gen 5, and we'll have an Ethernet MAC which will go up to 600 gig. And we will continue pushing the envelope of SerDes technology in this generation. We'll go up to 112 gig PAM4. And we'll have the next generation of ADC DAC integrated into our device. With that, this is our first Versal device, VC1902. It's been in the lab for the last couple of months, and we are shipping samples to early customers. This is our first Versal device, but not necessarily the biggest Versal device or the smallest. We'll have a pretty big range of small to the big. Just to give you some idea of the scope and size of this device, it has 37 billion transistors in TSMC 7 nanometer. as roughly 1 gigabit on-die memory, different memories, caches, and buffers combined. It has a AI engine array of 400 cores, which we'll describe shortly. And we have roughly 800 high-speed IOs, which can go up to 4.2 gigabits per second. And we also have 44 SerDes, each of which can go up to 32 gigabits per second. The picture on the left shows sort of placement of some of the key building blocks that we would go into today. The NOC is one of the new elements of Versal architecture, and it's basically a new packetized protocol for high-speed interconnect. All of our SoC building blocks, programmable logic are connected through the NOC. It's highly configurable in terms of the topology, routability, QoS, and so forth. And we would have a NOC compiler as part of a tool chain, which will generate use cases specific, especially the routing and the QoS. And the NOC spreads over entire chip. So to minimize the clock jitter and power, we use the clock forwarding as opposed to some one bandless big tree. Also, there are many nodes in the NOC, and not all use cases may use all of them. So we have aggressive clock gating as well as the data bypass for unused switches to minimize the dynamic power. The picture on the left shows the NOC topology in our first Versal device. Different devices will have different number of rows and columns. In this, each of the row and column provide of the order of terabits of cross-sectional bandwidth. Each row and column have multiple physical channels, and they get sized depending on use cases. But within each channel, we always have 8 virtual channels, and that's sort of the building block of NOC. And this device shows it's monolithic, but for multi-die SSIT devices, NOC will extend for die-to-die connectivity. So, okay, we have the NOC. What exactly do we do with it? Well, as you may know, compute acceleration is all about data movement. And the NOC is our backbone of data movement. Switching to memory subsystem, we have a unified memory system where all the agents, all the engines can uniformly access it. However, we can also customize it. For example, we can split it into 2 or more disjoint subsystems which are isolated from each other, can have their own independent QoS or other configurations. In this device, we have 256-bit memory interface, and the memory controller is optimized for both 64 and 32-bit granularity. This device has 6 PCI Gen 4 controllers and 400 gig Ethernet MAC. And the idea is, with the help of these high-speed interfaces, you can build a smart storage accelerator, you can build smart networking accelerator, and the placement, if you notice, is also following the data flow. The host is on one side, and the NVMe or other storage on the other side, or the networking on the other side. This is our second generation of C6 implementation in our devices. In this, we have home node support for coherent peer processing. We also have hardened L2 cache, so Accelerator can have caching capability, or we can extend the caching capability into programmable logic for lower level caches. We also have the C6 extended mode, which enables us to run at 25 gigabits per second as opposed to PCI Gen 4, which you may know it's up to 16 gigabits per second data rate per lane. With the C6, you get the coherent load store semantics from the host into the accelerator. On the process system, this is our third generation of process system we are integrating to our devices. But unlike previous ones, in this, all of our Versal devices will have the process system integrated in them. In this first Versal device, we have a process system with an APU, which is a dual-core application processor with coherency and a virtualization, where all the non-CPU agents could be virtualized through the system MMU in the APU. We also have a RPU, which is a dual-core real-time processor and can be lockstep and is capable of going up to the highest level of automotive safety, which is ASIL-D. PMC, think of PMC as a gateway into the chip for boot, configuration, security, power management, debug, and so forth. This is our gateway. Some of the key components of PMC is a dual triple redundant microblade subsystem, and a number of crypto accelerators for security. With the help of PMC, we have one of the most advanced root of trust in Versal devices in terms of authentication, where we support RSA as well as elliptical, and encryption, and the key management and storage. Also, we have for the voltage and temperature sensing, we have these distributed sensors this time, where satellite sensors are sprinkled all over the chip, and PMC aggregates them to provide sort of unified reading of the voltage, temperature of the device. For configuration and debug, which often tends to be afterthoughts, we have architected them as first-class citizens. For configuration, we have throughput improved up to 50 gigabits per second, which is 8 times over previous generation. For example, you can program a programmable logic kernel in less than 10 milliseconds. On the debug side, we have introduced a new high-speed debug port, which is a serial interface. And with the help of this high-speed debug interface, we can provide the throughput for both debug as well as trace up to 10 gigabits per second. And if you compare that to the JTAG we most of the time use, it's a huge step up. We also have the smart cable to go with the high-speed debug, but you can also use the debug infrastructure over the PCI. So we can plug into the host and use one of the physical function of the PCI to provide all of the debug resources, then you don't need the cable per se. Switching to programmable logic, in this generation, we have re-architected the CLB, which is the building block of our programmable logic. We have bigger CLB with improved local interconnect. And if you know how the programmable logic works, the global interconnect is critical. By having a bigger CLB with enhanced local interconnect, we minimize the need of global interconnect, thus improve the utilization of the resources. We also have introduced the idea of IMUX registers, where all the inputs have IMUX registers, so we can pipeline or time borrow to improve the frequency of the programmable logic. And this device has 900 kilohertz, which is roughly 2 million logic cells. We also have 158 megabit of distributed RAMs, which can be used to build last-level customized memory hierarchy. The DSP engine in this generation introduces the floating point for the first time for us. It also significantly enhances the fixed point operations. On the top right graph shows the performance improvement of one DSP engine over the previous generation, so it's somewhere between 2 to 3, depending on the type of operations. In this device, we have roughly 2,000 DSPs, which can aggregate up to 12 TOPS of peak performance. Oops, sorry. So give you a quick snapshot of our silicon bring-up. This is the snapshot after initial couple of weeks, so obviously we have moved from this. But just to highlight that all of our building blocks of all of our engines were doing pretty good in initial few weeks. This is our first 7-nanometer device. It's a lot of new architecture elements, a lot of other re-architected ones, but this has been really good bring-up so far for us. And with that, I'll hand over to Sridhar to go over AI engine and share some of the benchmarks.
Thank you, Sagheer. Over the next several minutes, I will give an overview of the AI engine in Versal. The AI engine is a key component of the heterogeneous system architecture that Sagheer talked about earlier, and it's an essential part of the adaptive compute acceleration platform. all the bandwidth that Sagheer talked about in the previous slides is consumed by an array of up to 400 AI engine tiles, or the processing tiles as we refer to, that can deliver a peak performance of 133 teraops per second. These processing tiles are enmeshed in a non-blocking interconnect mesh that can deliver up to 20 terabits per second of horizontal cross-sectional bandwidth, which itself is divvied up amongst a large number of streams, in this case, several hundreds of streams, that provides for the non-blocking cross-sectional communication. And all this, the compute and communication would not be served well without the appropriate support from a well-balanced memory subsystem. So the AI engine in Versal is supported by a distributed memory hierarchy, starting with up to 12.5 megabytes of level 1 memory in this chip. And these memories in each of the processing tiles is also shareable by the cores and the DMA of all the neighboring tiles in the 4 cardinal directions. In addition, these are banked to allow for simultaneous access between the local processors as well as the neighboring tiles to deliver the performance. In addition, the memories are equipped with a feature-rich distributed DMA that truly enables parallel compute and communication. Let's take a look at the compute here. So it all starts with the processor core in the AI engine tile. So this is a VLIW vector core comprised of 32-bit scalar RISC engine that is capable of performing up to 2 scalar operations per cycle with additional capability to stream data in and out, which is another set of operations. Among other things, it also has support for nonlinear functions like sine, cosine, square root, etc., that is well suited for signal processing workloads. And flanking the scalar engine is a 512-bit SIMD vector engine that is capable of performing up to 4 vector instructions per cycle. And these engines are provisioned with dedicated program memory and 32 kilobytes of data memory, which, as I said before, is shareable amongst its neighbors. And each core can address up to 128 kilobytes in that fashion. So all put together, these engines can deliver greater than 7 ops per cycle. So here we illustrate the rich support for multiple precision data types suitable for different workloads. So on the real world side, these engines can deliver from 8 single precision floating point operations all the way up to 128 int8 max per cycle. And on the imaginary world side, which is still real world computing, or the complex side, we deliver from 2 up to 16 complex max per cycle, where one or both operands can be a complex number. And this is, again, well suited for signal processing workloads. So let's spend a little bit of time on the memory subsystem that is supporting all this compute and communication. As I said before, the compute and communication can deliver only if you have the appropriate support from the memory subsystem in terms of both the memories and the throughput that can keep the AI engines busy. So we start with a large level 1 SRAM, which I talked about earlier, where data movement is orchestrated by a distributed DMA through an adaptable non-blocking interconnect mesh. And the AI engine is fed from, quote unquote, the external world relative to the AI engine from a larger memory pool of level 2 memory distributed throughout the programmable logic fabric through a large number of interconnects. And finally, the memory capacity needed for large workloads is provided for by external DDR memory, where data is actually fed, can be fed from any of the 4 channels of memory to any of the streams feeding the AI engines through a flexible crossbar topology. The flexibility of the crossbar topology also allows us to reconfigure the topologies. In this case, we illustrate a segmented crossbar topology, which allows for optimized allocation of both the memory and the throughput to the large number of parallel streams feeding the AI engines. Finally, I would like to mention about the multicast and broadcast support within the AI engine interconnect network that allows for very efficient transmission of streams data to several kernels running in the AI engine tiles. For example, the weights data can be efficiently transported to multiple kernels of a neural network. Looking at all this in the context of numbers, the memory capacity and the bandwidth ratios amongst the various levels of the memory hierarchy is well balanced to feed the appetite of the AI engines to deliver a very highly efficient AI compute engine. So to recap, the AI compute engine with the scalar and the vector processing cores, supported by an adaptable non-blocking interconnect that supports multicast as well as circuit switching and packet switching, fed from a distributed memory hierarchy where you have local memories which are shareable by the cardinal neighbors, the cores and the DMA of the cardinal neighbors, and distributed DMA that truly enables parallel compute and communication is what is enabling us to deliver a highly efficient compute engine. As you can see, we're able to realize greater than 90% efficiency on our cores, both for convolutions as well as DPD workloads used in signal processing. So how does it translate to some real-world benchmarks? So as you can see, we were able to realize between 5 to 7x increase in performance compared to our currently shipping products on both GoogleNet and ResNet 50 inference workloads. Now, the benefits of the heterogeneous system architecture is truly borne out in bringing out the capability to accelerate whole applications. We illustrate a list of applications here, all the diverse engines that Sagheer talked about, the scalar engines, the application processing engines, the fine-grained parallelism enabled by the programmable logic fabric and the adaptable intelligent engines with the appropriate memory hierarchy and the bandwidth distribution is enabling us to accelerate whole applications. For example, it could be video processing with video recognition or real-time analytics combined with any of the applications listed there is all enabled. And the key element of all this is deterministic performance and low latency, which was architected right into every component of the Versal architecture. And these metrics carry over to one application that we illustrate here in terms of how we take 5G wireless pipeline, particularly the digital radio section, and map it onto the various portions or the various components of the heterogeneous architecture, where in this case, the workloads are partitioned appropriately into the elements, the blocks, which are well suited to perform those portions of the workload. So for example, here the processing subsystem does parameter estimation and coefficient updates for the radio processing, and the bulk of the core digital signal processing functions like rest factor reduction and digital pre-distortion are performed by the AI engine here. So finally, this talk would not be complete without a mention of the programming frameworks. At Xilinx, we have been working to enable the simple design, compile, and run paradigm for the application developers. You develop your applications with standard high-level languages like C, C++ on top of standard programming frameworks like TensorFlow and Caffe, built on top of Xilinx-supplied libraries for wireless processing, AI, as well as other types of workloads like vision. And the goal is to be able to just develop the applications, compile, and run them. In addition, Xilinx is also developing architecture overlays that should enable raising the abstraction level to the point where customers are simply focused on application development. And supporting this paradigm is the underlying tool chain, where we start with the System C simulation platform, which, among other things, consists of the core instruction set simulator for the AI engine core, supported with the standard ARM compilers for the processing subsystem, the AI engine compiler, which is an essential part of enabling the AI engine applications, and the all too familiar Vivado kernel compiler for the programmable logic. And it comes with the standard SDK with support for tracing, profiling, and debugging. And to top it all is the system partitioner that enables the partitioning of the workloads appropriately into the different blocks of the heterogeneous system. To summarize, Versal is the first generation of the adaptive compute acceleration platform series. It employs a heterogeneous architecture, which we have talked about enough in this talk. It comes with a brand new software programmable AI engine, a ground-up design of a new high-bandwidth network on chip that Sagheer, I think, delved into a fair amount of detail, a processing system in all our Versal devices for the first time, Xilinx, and a re-architected programmable logic fabric. So that is what has shaped up into the Versal AI core, which is Xilinx's first 7-nanometer device that can deliver a peak of 133 teraops per second and a coherent fabric up to 25 gigabits per second, among other things. For more information, you can go to xilinx.com/Versal. Thank you all.
All right. Now it's the Q&A time. Please keep your questions short and one question per person. No questions? Maybe I will go first. So for this chip, I know that Xilinx has a PGA with 3D die stacking HBM in it, but this one doesn't contain HBM.
The first one doesn't have HBM, but certainly we're working on it, and then soon we'll have some more details. But we will have Versal devices with the HBM.
Okay. All right, the question.
Nathan Brookwood again. You mentioned that you support C6 in Versal. Do you have any plans to support Gen Z and CXL? I noticed that you're a member of all those consortiums, but when should we expect to see those showing up in your products?
Well, so maybe I can quickly go with Gen Z. Officially, we don't have any plan. CXL is like announced a month or so ago, I suppose. We're looking at it. We will have something in the near future to share. But at this stage, we are focused on C6. There is not much you can do with the CXL today or in this generation so far. But I think for CXL, we will have some more details in the near future to share.
Great, thank you.
This side, please.
Yeah. Thanks for a great talk. I'm Shrikant from Google. Quick question about the ratio of the interconnect delays versus the programmable logic that you see in this new 7-nanometer series, because in past devices, I've seen as much as 70% interconnect to 30% logic. So is that something you can comment on?
So let me see if I understand the question. You're talking primarily with regard to the programmable logic or mixing with the NOC?
The programmable logic.
Well, so the idea of having this bigger CLV with the more localized interconnect is really to reduce the burden on the global interconnect and thereby reduce the congestion on the global one. So hopefully we should get better utilization for the same application as compared to before.
I think in addition, the NOC that Sagheer talked about also should enable dialing down a lot of the latencies that you would otherwise see, just purely going through the programmable logic.
Thank you.
Right, please.
Hi, thank you. It's Wei from Alibaba Damo Academy. Very interesting topic. I want to ask some question about the 5G wireless. You mentioned port 5G wireless on this platform. Can you give more information about that? Because on this slide, I saw some words like LTE 20. I guess that is IoT 20 megahertz carrier aggregation, right? You have 4 or 5 different carrier aggregation into different channel. And also, can you give some information about decoding, demodulation? Because it seems like you can do the OFDM based, with FFT and filter. How about the decoding and demodulation? Thanks.
So actually, I would defer that question to We have a panel of experts backstage. After this talk, we can come and share more information on those questions for you.
Yeah. One more question, please. Yeah. Over there, please.
Hi, this is Zaid Samuel from ARM. Can you elaborate more about the non-blocking mesh? Because typically a mesh topology is more blocking as compared to a crossbar.
Well, so if you look at the different traffic types, the idea is you want to be able to isolate them from each other so one is not blocking to the other. And for that, we have so many of these virtual channels where each traffic type gets assigned a number of virtual channels, and they will be isolated from each other in terms of making forward progress.
Okay, thank you.
One final question. Last question, please. Yeah.
Hi, this is Brooke Trinity, and great presentation, by the way. So when you discuss heterogeneous acceleration, I believe I saw genomics plus AI, database plus AI. So are there workloads disjointed or are they mixed?
Let's get to the question, please. Yeah.
So are they, I'm asking the question, are they, when you say genomics plus AI, are we talking about disjointed or mixed workloads?
Well,
Because
maybe I think the key is really the AI is kind of a tool, can be used in any of number of applications, right? If you do, for example, something related to some of the examples there, not sure which one you follow, but pick any of those. There's some pre-processing, there's some post-processing, there's some other stuff. That's the application. Part of it is AI. So what we are saying is that we are more focused on more of the end-to-end, and of which AI is one of the parts.
AI inference is not the whole application. To paraphrase what Sagheer is saying. So some of the pre-processing, like DNA sequencing, etc., can be accelerated in parts of our device, and the analytics or learning aspect can be performed by the AI engine.
Thank you. I'll follow.
All right, thank you. Let's thank a speaker again. So our last talk is from Intel, and the speaker Ofri is an Intel fellow at Intel's AI product group, leading the Inference architecture. He has more than 30 years experience in processor architecture, including Skylake and Sandy Bridge, Sentinel, CPU, and so on. Let's welcome our speaker from Intel.
Thank you, Johan, for the introduction. This is really exciting for me to be here this morning. Actually, it's not morning any longer. And talk to you about some of those things. So like Johan mentioned, I've been over than 30 years in this field of processor architecture. And all the way from the Pentiums and the Centrinos and the other chips that we did at Intel. And this was very, very hard work to get the performance year after year to, and you saw yesterday the general purpose people talk about all those thousands of applications that you need to make sure that you don't compromise and you push 2% here and the other one goes down by 2%, and then you end up giving 17% per generation and you're very happy, and this is a great achievement and a lot of work, but this is very, very, very hard and not always appreciated by the customers. And then 10 years ago, I moved to work on parallel architectures. This is where areas where performance really matter for the end user and not just for marketing campaigns. And this is really different. So graphics, for example, was one of those areas, very, very niche though to gamers and some of the content creators. And then HPC was also very, very interesting, but also niched. And then in the beginning of and machine vision and all those things, and then in the beginning of this decade, with the rise of deep learning, I think this really sent a shockwave that people started realizing little by little the importance of this, not just to the algorithmic level and to in so many industries, but also to the chip architecture, because we were able to actually build parallel architectures that would be applicable to a very wide range of applications or of problems that people want to solve. So if you remember the charts from Lisa yesterday with narrow and shallow and broad, and then going higher and higher, but being less applicable, deep learning really makes allows us to eat the cake and have it in a way such that we can design a parallel architecture that is very, very efficient, very, very high-performing, exploit parallelism with the underlying architecture and hardware design, but at the same time is very, very useful and very applicable. And this is really I think people are realizing it. They've realized this over the last few years, and this is why we see all those different architectures and talks and papers, et cetera, et cetera. And this is very, very exciting. This is really a new era for computer architecture. So today I'm super excited to talk about Spring Hill, which is actually what we have built to solve this problem and to exploit this parallelism. So you can see behind me on a picture of a Spring Hill, actually, and I was afraid that the slides would not come up, so I actually brought it with me. Where is it? There it is. It's very tiny. This is, I don't know if you probably cannot see it, row number 3 and beyond, but this is really this is an M.2 form factor card with a Spring Hill. This is one of the form factors that we are supporting, and I'm going to talk about it. But we are able to pack close to 50 teraops of compute, of very, very dense compute in such a tiny form factor, which is traditionally used for SSDs and the likes. So very, very exciting product, and I want to tell you a little bit what we did and why we did and how we did it. But before I go there, I want to recognize 2 of the most brilliant people that I've been working with in the last 30 years, which are actually here in this audience, Michael Behar and Bharat Daga, who were 2 of the key architects on this product, and you can probably talk to them and pick their minds during lunch break and other breaks. They are sitting here in the audience. So let me now dive into the presentation and tell you a little bit what were our goals when we started this program. So the first thing that we realized that we want to really optimize the architecture for performance per watt, not just do the performance, push the performance, and at whatever cost, and not just push the performance and worry about the power later and maintain it somehow. Really, everything that went in qualified by this metric of performance per watt, and we picked the number 5 or close to 5, as close as possible to 5 tops per watt. Tops per watt is, on one way, you can say this is a pretty meaningless metric unless you build a really, really balanced machine that can really exploit and get with the efficiencies close to that. The way I look at it, this is a necessary but not sufficient. You need to get the speeds and feeds, but you need to get the machine and the architecture such that many of the workloads, or most of the workloads, or actually all the workloads, we get as close as possible to this number, and we ended up shooting for 4.8 tops per watt, and I'm going to show you more details. So this is the first kind of takeaway that we started with, is this tops per watt or performance per watt, and not any other metric by any other means. The other thing is it turns out that in chip design, where you shoot your design to is what you get in the end, in terms of you end up getting very, very different trade-offs if you shoot it high or you shoot it low. So we figured that we don't want to shoot it for the sub-1 watt range, for battery-operated devices, which would make it hard to scale this design. On the other hand, we didn't want to shoot it to the hundreds of watts that some of the people do. We thought that's going to be beyond the need of efficiency in terms of cost of operation, cost of maintenance, power efficiencies, etc. So we picked this 10 to 50 watt range as the range that most people would just use standard infrastructure, standard PCI form factors, and be able to seamlessly upgrade their systems or data centers with this capability. So that's the second thing that we had in mind. And then the third thing is something that a lot of people talked in this conference about, this trade-off between programmability or flexibility, if you will, and the efficiency. And this is really a hard trade-off. And what we wanted to achieve is basically both. To have a design which is as efficient as this 5 TOPS per watt as the North Star that is guiding us, on the other hand, doesn't compromise the flexibility that people need. And there are different ways how to look at flexibility. If you start from the ground up by building very complicated ISAs and then building the microarchitecture on top of the ISA, and then the workloads and the applications, etc., this is probably the wrong way to go. We started from the top. We looked at the workloads. Deep learning allowed us to focus on several aggregation, pivotal algorithms. You saw, for example, the Facebook talk yesterday that talked about some of those workloads and other examples. So we started from the top, and then we figured out what kinds of flexibility we need to have and what kinds of programmability we need to have in order to really provide enough for the people to operate in. So that's like the third very important thing, and I'm going to show that. And then performance matters, but for the data center customers, money is the thing that matters the most. And then you need to build your part with all the features that allows them to reduce the cost of operation. So things like remote debug, error correction on the memory path and on others, etc., are very, very important. And then last but not least is the software, obviously. The parallel hardware is especially important. You have so many tens of thousands of execution units that needs to be orchestrated and mapped onto, and you cannot do it without this. In fact, I think the parallel compiler is probably the most intellectually hard problem to solve here. And I'm going to show you what we are doing. So here it is. This is this new baby, a concept picture, but it includes all the important elements. So in the heart of it, we have those 12 inferencing cores. Those are cores, we call them ICEs, for inferencing compute engines. Those cores are really optimized for inferencing workloads, and they can work autonomously, each one solving a network or multiple networks, or running different copies of a network. And they can also work collaboratively. We have 12 of those in Spring Hill. They can work collaboratively to solve a bigger problem or to solve together a problem if you want to shorten latencies, etc., etc. So there's multiple options how to operate this structure. They communicate through a shared fabric, a coherent fabric with a 24 megabyte hardware managed cache. It's hardware managed, but it also provides provisions for the software to let the hardware know what kind of expectation it has in terms of service level priorities for this surface versus that surface, etc. So it has the benefit of hardware managed, very low overhead synchronizations, etc. On the other hand, it has some provisions for the software. It has a 24 megabyte cache that assists the data transfers. And this is all sitting in the heart of Spring Hill. And then on this same fabric, we also decided to put 2 fully fledged IA x86 cores, Sunnycove cores. These are the latest cores from Intel that goes into the most advanced chips from Intel. And we have them on our accelerator die, very close to the ICE engines, sharing the same fabric and the same cache, and very fast communication between the two. The IA cores basically runs the orchestration software, the runtime software that orchestrates what the compiler has dictated ahead of time. But they also provide headroom for the user, actually, to put whatever he wants to put in with probably the most programmable machine that you have on the planet. So this is all very cool. We also have some hardware synchronization mechanisms that we have built in order to assist. Usually in those kinds of devices, you have the device driver. It's a lot of overhead to go back and forth. We have offloaded and accelerated a lot of this orchestration and synchronization work to a hardware unit that sits on die and allows us to have a really, really efficient communication between the ICE cores, the IA cores, and this whole continuum. So this is all based on and built on Intel technology, 10 nanometer process node, and this also we were able to reuse and borrow a lot of the technologies that we have developed in Intel for other power-constrained problems. So I mentioned for example, the M.2 form factor, which is roughly speaking 10 watts form factor, which is roughly speaking what you get in a laptop. And a lot of the power management and power delivery and other technologies that are used over there are very useful over here as well. So we are using some of those very advanced technologies for example, for power management, we have a very, very sophisticated dynamic power management controller on this chip that allows us to dynamically shift the power budget between the execution cores and between the memory and the execution core, depending on the workload. So the way it works, the compiler is actually, as opposed to your normal operating system and software where you need to figure out everything in runtime, here we can do a lot of prediction ahead of time and map the work with the allocated power budget, and then during the runtime, we have to just carry out the plan, if you will. So that's that part. And this is a standard PCI device. It connects to a Gen 3. It provides either by 4 or by 8, depending on the form factor. It provides sufficient I/O bandwidth for us to operate on all of the workloads that we are working together with our customers and partners. And it also has 128 lanes of DDR, LPDDR4 in this case, running at up to 4.2 gigatransfers per second, and we can support a 2x64 or 4x32 configuration. The memory is very, very important part. We will talk about both the memory and the compute, but the memory, I already mentioned the 24 megabyte. But this is not the only part. We also have additional 48 megabytes, so total of 75 megabytes of SRAM on die, which is mostly a distributed SRAM within those ICEs. Each one of those ICE boxes contains 4 megabytes of memory. Basically, with this 75 megabytes, we are able to absorb most of the memory traffic. So in most of the workloads, most of the memory traffic is actually on die, and this is an important piece of being able to get those power efficiencies. So yeah, moving in the wrong direction. So here is the closer look into the ICE engine. This is really, inside this machine, you really have 2 engines that are programmable, but very different than one another. In the center, this is the the deep learning compute grid, which is a 4 kilo Mach grid. I'm going to talk about it in the next slide, but it's really allows us to run the majority of the compute on it in a very, very efficient manner. It supports all of the important data types that you would expect to see, including floating point 16, int 8, all the way down to even 1 bit. So we can get very high throughput in 1 bit, 2 bit, 4 bit, 8 bit, and FP16. And then it has a lot of memory inside the compute grid to buffer the data movement. And all that is coming in the next slide. But next to it, there's another compute engine, our programmable vector processor, which basically allows us to run very tightly coupled with the matrix DL compute grid to run operations that are not available on this compute grid. So between those two, overall, we get a very, very good coverage of everything that we need to do. And this is why this is a whole subsystem with a controller that basically orchestrates all the data movement between the two engines and outside and inside. The 4 megabyte SRAM that I already mentioned can be used to either store persistent data. On the very right-hand side, you can see a picture. For example, if we want to optimize for latency, we can break the network and the layers across multiple ICE engines, putting the model parameters or the portion of the model of the parameters that are relevant to this particular ICE in its own SRAM, and therefore they live there forever until we update the model or change the topology or something like this. And then if we optimize for throughput, we can apply a different strategy where the models sit, for example, in the shared cache, and they all read from the shared cache, and they use the 4 megabyte buffers to store intermediate results and never go out for layer-to-layer communication. So then even a closer look into the DL compute grid. I think this is, so people talked here about, this is about all sorts of structures. This is a very, very unique structure in a way that it provides 4 dimensions of parallelism. So in a way, this is a 4D grid that we have a very elaborate data path that allows us to broadcast across those 4 dimensions. And basically, people talked here in the last few days about the fact that we want to minimize data travel and we want to maximize the reuse, and this is what these structures allows us to do. Basically, every element that we read, we use it multiple times across the 4 dimensions of parallelism that we have over here. So that's one important piece. The other important piece is those input and output memory buffers that you see, that basically allows us to maximize the time that the data sits, the computation sits inside this box and never goes out. And we go out after we have reduced it dramatically, so the traffic going out of here is dramatically different, and I'm going to show you some figures a little later. So another important piece is the post-processing pipe. And this is important twofold. First of all, we harden some of the most popular operations, but it's not just about hardening ReLUs or max pooling or things like that, which is important on its own merit. It also prevents us from, allows us to not do additional memory round trips in order to do more and more post-processing operations. So we can fuse layers and we can fuse whatever makes sense together with this post-processing pipeline. And this whole thing is controlled by a controller that sits on the left-hand side in this picture. But the thing is that it's very, very programmable, and it allows us to map the 4 dimensions of parallelism that I talked about to different levels of parallelism in the problem. So different problems will lend themselves differently, and the compiler will figure out how to map the dimensions of the problem to the dimensions of the hardware and get the maximum out of it. So this is really a very careful co-design between the hardware and the software. And then next to it, sitting the vector processing engine. This is built on a Tensilica P6 technology, which we have customized and included a lot of new operations that are useful here in deep learning. And the thing about, so this is a very capable machine, and we are able to basically build algorithms, like very sophisticated and unique algorithms that customers might want, can be built upon this vector processor. And there is a very tight collaboration and synchronization between the 2 engines via the internal fabric and the tightly coupled memory that we have inside the ICE. So talked a lot about the compute part of things, but even more important is the memory part, because we know that the energy that it takes to move the data is far greater than the energy that it takes to compute the data. So we have four hierarchical levels of memory that the Spring Hill machine supports, and they go increasingly in order of magnitude, increasing in the bandwidth that we can provide. So starting from the DDR that the machine supports, LPDDR4, which is like the 1x, so 60, 70 gigabytes per second, depending on the workload. And then the last level cache provides roughly 10x of that to the different ICEs. And then inside this distributed SRAM provides close to 100x in terms of aggregated bandwidth that we can support. And then if you look inside into the compute engines, you have terabytes of data per second that you can really absorb. The programmability story is very important here. So the DL compute grid on itself is very, very configurable and very, very flexible in its ability to adapt to different algorithms. We have the tightly coupled vector engine with a very elaborate ISA that we can use for maybe 10% or so of the very, very tightly coupled within the layer or very close to the layer to get the entire functionality right. And then the IA cores, which sit on the same fabric and allows us to basically do very sophisticated algorithms like your own custom sort or ranking or whatever algorithm you want to do, you probably have it already built and you can deploy it over there. So then here are the performance numbers that we are seeing. We have a lot of work on performance. This is one example. This is ResNet 50. This is something that we have, one of the workloads that we have optimized the machine for. And so the Spring Hill is delivering 3,600 inferences per second. But the great thing about it that it's doing it only consuming 10 watts of power of the entire SoC. So overall, this is 360 images per second per watt, which is pretty amazing. And this is very close to the goal that we've set up in the beginning to get too close to this target that I was talking about. The other thing is that if you look at parallel architecture, one of the ways to examine the robustness of the architecture is to see how it scales. So when we scale from the machine from a 2-core configuration to a 12-core configuration, we get linear scaling, or close to linear scaling, which means that the machine is very, very balanced, the memories are balanced, the fabrics are balanced, and the entire thing is orchestrating very, very, very nicely. And then the chart on the right is basically here to tell the story that is, this is not slam dunk. We have done a lot of work to get to this number, this 3,600 number, and you can see some of the steps that we have taken over there, starting from the 4D parallel compute grid, with the distributed local memory, with some accelerations that we have done in order to fit to the right SIMD widths, and to accelerate some of the synchronization primitives and the data movements, and to fuse the layers, all the steps that that I described, and takes us up the ladder to get to the 360. But the thing is that what we found out, that after we have squeezed this and optimized this part, this was applicable to many, many other workloads. So actually, this hardware and those optimizations that I'm describing over here are broadly applicable to many types of workloads. So this is one example. We are going to, as part of this MLPerf next revision, we are going to submit many other workloads that we are working on, and stay tuned for that. And I want us to summarize by saying that the key messages, basically, this is really best in class in terms of performance per power. This is what we, but to a wide variety of deep learning workloads, which provides an even greater ability to solve, for people to solve problems. So all in all, this is really eating the cake and have it. We are very, very happy with it. Like I mentioned, we have the silicon in-house over here, and we gave it to some of our leading customers who are tailoring and building their software as we speak with our chips. So this is all great. And we have, obviously, one of the things, I keep calling it Spring Hill. The official name is NNPI, Neural Network Processor Inference 1000. This is just indicating that there's more coming, this 1000, so there's more coming, and we have 2 more generations in the work. Really, really exciting, and thank you for listening. And we still have some time for some questions, right?
All right, thanks, Speaker. Because we are running out of time, I will take only 2 questions, 1 from each side. And if you have more questions, please come to the stage to continue, okay? Question from this side first. Okay.
Thank you for the talk. This is Yu Hao from Alibaba Demo Academy. I have a question is that you have 75 SRAM in total. I think that's probably enough for ResNet. However, it's a clear trend that neural network models are getting bigger and bigger, and the increasing SRAM is not a scalable solution. So how can you give us some insights that how can we tackle the future models?
Yeah, I think this is a great question. And we recognize the fact, first of all, with the Spring Hill 75 megabyte SRAM, we can solve many, many, many problems. So this is great, I think, for our current times. I think for the future, there's multiple things that you can think of doing. And this is probably a deeper discussion that we can have. And this is something that we are definitely looking at. And hopefully, next year we'll be able to talk about some of those. But today, with Spring Hill, the 75 megabytes are very, very extremely useful for many workloads. I think this is what I can say.
Okay, thank you.
Okay, one last question.
Yeah, so you showed tops of 2 to 4.8 tops per watt. Is that int 8 or?
Yeah, this is the performance that we get for int 8 operations. Yes.
Okay, I think I had a subsequent question. Is like, is it also taking into account sparsity?
Let's get it down. One more people waiting for you.
Okay.
We can do the rest of them here. Let's take one more question here. Right?
Thank you. Quick question. Given your ML focus, is there a reason why you didn't incorporate bfloat 16 into your design?
Yeah, so bfloat 16 we are not supporting on Spring Hill. But I think I would say I can say 2 things. I think that with the data type mixture that we have that I showed you, we can solve all the problems today pretty efficiently, very efficiently actually. I think bfloat 16 opens more opportunities for future, and we can discuss it later.
All right. All right. Let's take our speaker again. And okay.